let's have a head start. Yeah, let's start 1 minute early, then we have 1 more minute to enjoy the Rydberg quantum computing platform, which we are working on at the University of Stuttgart, next to this place. It's just a few S-Bahn stops down the metro line. What I'm going to present to you is the status of the field, the status of our activity, and the perspective, where I think this is going to go. Yeah? Now, we do have a demonstrator project that is funded by the BMBF, generously funded by the BMBF, and it's the first one in Germany that is using this platform. By now, there are several other demonstrator projects in other places, like Munich, Hamburg, and also Tübingen, Kaiserslautern, but this one is the first one, and it is sort of the most advanced one. And if you want to get more information in general about our activity within this framework, we are the Quantum Land, and there's our stand, and you get even more information there. Okay? You see, this is Baden-Württemberg, this is Stuttgart, and there's a Rydberg electron orbiting the whole state. Yes. Now, Rydberg quantum computing is one platform out of many platforms, yeah? And I have this outdated map here that shows the neutral atoms in optical tweezer arrays, and that's what we are going to talk about, actually. In contrast to superconducting qubits, ion traps, NV centers, and many more platforms. But I want to convince you that we think that the Rydberg platform has the potential to outperform all of them. Okay? It's maybe a provocative statement. We can come back to this at the end. But I want to convince you that we are actually making extremely nice progress. The lab that you could have seen in Stuttgart here looks more or less like this. So what you can recognize is that there are no cryostates here, but a lot of lasers, a lot of light. Yeah? So the platform, the Rydberg platform, uses solely laser light to cool, to prepare the qubits, to operate the qubits, to do the algorithms, and to do the readout. There is no wiring issue, no electrical circuits anywhere. It's a laser show. Okay. So the base technology for us is laser cooling. Yeah? I don't go into any detail here, but with lasers you can cool matter down to temperatures as low as 1 microkelvin or below. So a factor of 1,000 lower than what you can ever do in even the best dilution refrigerator. Okay. And this is a well-known technique. Many people have received the Nobel Prize for this, and we are just using this technique. Yeah? And if you have atoms, neutral atoms, as cold as a microkelvin, you can easily trap it in a single focused laser beam. Yeah? As you can see here, the atom comes in, it gets trapped in the focus, and then you can maybe excite it to the Rydberg state if you want. Okay? And that is going to be the single qubit case. And what you see on the right is an array of such tweezers filled with atoms, first in an irregular pattern, then after some sorting in a regular pattern. So you see, these are hundreds of qubits. Actually, by now, 300, 400 qubits have been realized that are spaced here on the length scale of a few micrometers. And therefore, we can easily optically address them with regular linear optics. Okay. So this concept of tweezing or trapping atoms in these arrays was first pioneered in one dimension by the Looking group in Harvard, where you see a line here that is first filled, then you switch off the empty traps after you took a picture, and you move the rest together, and then you have zero entropy in your chain after that process. That also works in 2D. That was shown by the Paris group, and even in 3D. And as you can see, this was also done by the Paris group. Yes? So it is possible to arrange the qubits in a three-dimensional pattern. Okay? And what is more, these patterns can be dynamical. Okay? And what you see here now is work from the Looking group, where you see these qubits moving in a 2D plane, and at certain positions you do 2-qubit operations. Okay? Whenever there's a red circle here, That's where the 2-qubit operations happen. So guess what this was, actually? Because if you have a 2D plane and the time as a third dimension, what you can realize is a torus. And what this was the algorithm for the first demonstration of the toric code that lives on a torus. Okay? So with this dynamical connectivity that we have in this platform, we can, generate algorithms or realize algorithms that a static platform can never realize. So there's an algorithmic advantage. There's yet another algorithmic advantage. If you move these qubits around and you let this central qubit here interact with 2 or 3 or 4 next neighbors, you can do what is called a many-body gate, which means that you entangle one qubit with n other qubits around it. Okay, whereas normally you have to do a lot of 2-qubit gates. Here you can do it in one shot. Okay. Now, what's the status, really, in terms of fidelities, let's say? I mean, there are lots of figures of merit, but one important is the infidelity, which I plot here in the logarithmic scale, yes? And it's the infidelity, in this case, of a Bell state preparation, which is the heart of a 2-qubit operation, okay? And you see, as a function of time, the trapped ion community started first, yes? And they came down with their infidelities over time. Later, the superconducting platform started, but they also come down now to fidelities in the best papers that one can find. Yeah? In this case, with 2 fluxonium gates, which is not the normal gate. It's usually a transmon gate, but still, they can reach 99.9 fidelities. So what about the Rydberg platform? We, again, started much later, but you see that the best fidelities that have been achieved here are again on the 99.7% level, yeah, which is really a competitive thing, especially if you compare it to the commercially available platforms. Okay. So to summarize this, more than 300 qubits have been realized with the fidelities in the 99s point something. There are 5 startups. Actually, one of them you find back there. It's Plan QC. It's the latest of these startups, the first German one. The French one, Pascal, and a lot of American startup companies on this platform. Of course, many university groups, and in Germany we have BMBF demonstrator projects, ours being the first one, but as I said, there is now one in Munich, Tübingen, Hamburg, and Kaiserslautern as well on this platform. These are the fidelities. Again, we understand our errors. We know we are dominated by Pauli-Z errors and qubit losses, so we know exactly what kind of strategy for error correction needs to be taken. And now comes the atomic physics part. Yeah? These are neutral atoms. So there are actually various ways to store a qubit in one single atom, yeah? Because there are many different transitions there that you can use for storage. And in one atom, you have many possibilities. So the standard one in the atom we are using, which is an Earth alkali atom, is the optical qubit, which is the one that is used in optical clocks. Yeah, they have the best coherence times ever to define our second, actually. Yeah? But there are more possibilities. You can use a nuclear qubit. That's this picture here. You can use the fine structure qubit. In principle, nobody has done that. That is the electron spin. Or you can put the Rydberg atoms in a circular state, which is very long-lived, and use this as a qubit. And these two ones are the unexplored qubits in the Earth alkali atoms, which is the subject of our project here in Stuttgart. Okay? And I will try to motivate why we think these qubits are good. Yes? So if you go to the clock qubit, the very long lifetime can be seen here in a nice paper by the Gilla group. You see this is a second time scale. Yes? So the coherence of these Rabi oscillations between the ground state here in a strontium atom and this excited clock state can live for half a minute or more. Yes? On the other hand, you see it takes about 100 milliseconds to do a single spin flip operation. Okay, that's a long time. Yeah? But this is a perfect storage qubit. Yeah? If you need long memory times, for example, for readout and error correction, this is perfect. Yeah? But we need another very fast computational qubit in order to match the timescales of the 2-qubit operations, which are on the 100 nanosecond timescale, so 1,000,000 times faster than this optical qubit. Okay? And that's the purpose of the fine structure qubit, which actually lives between this upper clock state and another very long-lived state, so-called triplet P2 state, which differs just by the flip of the electron spin. Okay? And this lives actually 17 terahertz above the lower state, and we are coupling this by a Raman transition, again by just 2 clock lasers that we frequency lock on an optical frequency comb. And I can show you here just very recent, very first oscillations. This is by no means anything competitive, but we have found this qubit, and we are starting to investigating it now. Okay. And you see this qubit is going to be extremely useful because it matches the timescale of the Rydberg gate operations. Okay. In order to address all these different frequencies that we need in the experiment, we have Toptica as a partner in our project, and they deliver this kind of racks here, which deliver 10 wavelengths. In principle, all of them can be stabilized to 100 hertz or below, because they are locked to the frequency comb. So these are extremely stable frequency lasers, and they are not on our optical table anymore. They are just in these racks, and we just get optical fibers that we can distribute on our optical table to work with. Okay. So then how about the Rydberg state itself? Of course, that's the magic of the whole thing. I mean, you need to have very strong interactions. So you can excite this from this triplet P state with a single photon in the UV. That's 317 nanometers. And you can again see very high finesse or high fidelity oscillations for a single atom or for a blocked pair. And this measurement down here is directly the Bell state preparation if you stop it at the right moment. Okay? And you can learn from this that the typical gate time, as promised, is 100 nanoseconds, and the coherence time is 10 microseconds, or a little bit longer, maybe 20 or something. So that's nice, but the 20 or 50 microseconds is actually short. So can we do something about the coherence of this Rydberg state? After all, it's a very excited state, and it has a limited lifetime. And that is the ultimate limit of the performance of the whole Rydberg quantum computing platform. And that's why we have decided to make a move to also excite other Rydberg states, so-called circular Rydberg states, where the electron never sees the inner core anymore and therefore has a much, much longer lifetime. Up to 100 milliseconds or longer is possible. Okay. So a factor of 1,000 or so. Yes. And I'm proud to advertise the work of Florian Meinert at our institute, who has shown with his team, and these guys are also over there at the stand, that we can prepare these circular states and we can see Rabi oscillations. And also this is a very recent result, just a few weeks old. Yeah? Okay, so we have realized this other second Rydberg qubit. If you want to know more about our work and our platform, you can just go to this website here. As I said, I mean, our platform has no wiring issues, nothing. It's a laser show, yes? And you can see this here in this little movie. Yeah? It's a lot of laser pulses that are following each other. If you go to this website, then you can also have access to the Rydberg quantum computer, where you actually also find a drag-and-drop programming surface that you can use over there on the screen, yes, and realize your favorite algorithm already now, yes. And this is connected at the moment still to an emulator, so it's limited, of course, in the number of qubits to about 30. But you can nicely see, and they will demonstrate it to you over there, how error correction works, for example. Yeah? You take a certain circuit, you introduce an operation, and the outcome doesn't change. Yeah? That's what you can try yourself over there. Okay. But of course, the plan is to remove this emulator and replace it with our experimental setup. Then we should be able to go to 300 or 400 qubits that you can also access. And the timeline for this is about still 2 more years or so. Yeah? Actually, if you think about this platform and all these different algorithmic advantages that it has compared to the superconducting platform, it is clear that the normal compiler structures that are provided by Qiskit, for example, are not sufficient. And that's why we have teamed up with HQS in Karlsruhe. They optimize the compiler for our hardware structure. And you can actually, let's skip that, you can see that this compiler is actually performing better than Qiskit, even at the highest optimization level. Yeah? So about, the number of qubits that you need, for example, for a quantum Fourier transformation on this platform can be reduced if you use the right structure in your compiler. And what is more, if you are then converting it into computational speed, the HQS compiler outperforms, of course, Qiskit as well, actually by about a factor of 10 or so. Yeah? With this, I would also advertise this platform again. You also find introductory material, tutorials, actually on the high school level, where we have tried to avoid even things like complex numbers, okay, to describe what is a qubit, what is a gate operation, how can you build a Schrödinger cat with this drag and drop programming device, and so on. So if you are interested in that, like outreach and learning about quantum computing, you should also visit our web page and click on tutorials here. Conclusion. I have more time. I have bonus material, okay? Conclusion is that I really believe, as I hope I could convince you, that the Rydberg quantum computing platform has the potential to outperform all other platforms in terms of scaling, in terms of the variability of the structures. We can even go in 3 dimensions, for example. And in terms of the specs, like fidelity, dynamical connectivity, depth of the circuits, and so on. Okay. Now comes the bonus material, because you sit here and you ask yourself, Rydberg-Atom, what is this? I have maybe heard about atomic physics. Oh, I should not forget to mention the team, of course, here. Sorry about this. They are actually here and here. This is our team in the quantum land at the University of Stuttgart. But the bonus material now is about what is a Rydberg-Atom and why is it performing so well, you know? We need to have very strong interactions between these atoms that are switchable and coherently controllable. How do we do this? Yeah? These are, after all, neutral atoms. They are not ions that are sort of interacting by the static Coulomb interaction. Okay? So here you see Johannes Rydberg with his famous formula, and actually one of the typical textbooks about the physics of Rydberg atoms. So if you want to learn more about it, I can just recommend this book by Tom Gallagher here. Rydberg atoms then are atoms where the electron is in a very highly excited state, which is described by a quantum number n, the so-called principal quantum number. In the ground state, this principal quantum number is 1, but you see from his formula that there is an infinite series of bound states for this electron. And as you are exciting the electron from state to state, the orbital of the electron just grows in size. Yeah? Here you see this, yeah? That's n equals 1, 2, 3, 4, and then eventually the electron gets lost, it gets ionized, but before it gets lost, there is an infinite series of levels. Now, nothing is infinite in physics. The question is, how far can we go up in reality? And in our experiments, we have shown that we can go up to n equals 200, okay? What does this mean, 200, or maybe 100, yeah? The important information is, what is the size of this orbital? The orbital size scales with the principal quantum number squared. And the rule of thumb is, if you have n equals 100, then the orbit is 1 micrometer. Think about it. I mean, a normal atom is 1 angstrom, okay? This is 1 micrometer, okay? So 10,000 times more, yes? And as a consequence, the dipole moment that can be induced in this atom is also larger. If it's a static dipole moment, it will scale with n squared as well. Now, if you have two dipoles, they are interacting with a scaling law that goes like n to the fourth power. And as we are usually doing van der Waals interaction, which now for the experts is sort of the second order dipole-dipole interaction, it goes like n to the 11th power. So the normal interaction between two atoms in the ground state is enhanced by 11 orders of magnitude if you enhance the principal quantum number by 10 only. Okay, but we go to 100, so it's 10 to the 22. Yeah, it's a crazy number. Yes. Good. So this is the scaling of the interaction. So you think about two atoms sitting at a distance of a few micrometers that you can easily resolve in the microscope objective. And now you can excite these Rydberg atoms, and that's, of course, due to the advent of powerful and very spectrally very pure lasers. So it's laser technology that allows us to excite these Rydberg atoms in 100 nanoseconds and de-excite them, which allows us to switch this interaction that is extremely strong and long range on and off at will, and we can also do this in a conditional fashion. So, for example, only one of the two qubit states gets excited, whereas the other qubit state is left alone. This conditional excitation to the Rydberg state is the crucial ingredient for all the gate operations that we are talking about. Okay? Good, so it's conditional, switchable, and long range. Yeah? In an ion chain, you cannot switch off the Coulomb interaction. Yeah? But here we can switch off and on a very fast time scale. Yeah? And here you see another plot of the interaction strength in an extreme logarithmic scale because of this extreme scaling. You see that dipole, the normal van der Waals interaction is way down here. It's actually at these distances of, let's say, 1 micrometer, totally negligible. So these ground state atoms, and that's where the qubits live, they do not interact at all. It's like zero interaction. And if we excite it then to a Rydberg state, we can flip the interaction on and we can flip it off again. And now, of course, you have to think about clever schemes, and there have been also proposals actually from our group on how to use this in a very robust way, yes, to get gate operations that are not sensitive to technical errors and so on. Okay, but that's the basis of the Rydberg platform. Okay, and with this, I would say I ask you to ask questions. Yeah? There are still a few minutes left, but if you have questions, I'm more than happy to answer them. Yes, please.
What is the typical time scale for gate operations?
Yeah, so the question is about the typical time scale for gate operations. The 2-qubit gate operation can be between 10 and 100 nanoseconds. So the record values are it's in the nanosecond time scale. It's a matter of laser power. So if we get more laser power, we can drive it even faster. Yeah? The single qubit operations depend on the qubit, as I tried to explain. Some qubits couple stronger to the light, some couple less strong. The ones that do not couple very strongly are very good for purposes of storage. Other ones are very good for fast computational tasks. Yes, but the one that we have demonstrated here can also go on the 10 nanosecond time scale. Yeah? So that means, I mean, you can run 10 to the 5 of these operations easily in a single experimental run. Yeah? Please. Yes, you can move them around. Of course, yes. So you have to, and that's now a task for the compiler. Yeah, you can ask yourself, okay, there is a cost in time for a motion of the qubit. Yeah, and you have to ask yourself, is it more favorable to move the atoms around And you see the time scale running up there. Yeah? It's about 1 millisecond, the whole movie. Yeah? So compared to the 100 nanoseconds, that's slow. Yes? Compared to the storage qubit, that's actually very fast. Yeah? So now you can replace this movement in an array by a lot of swap operations. And then the compiler has to optimize whether it's worth going through, I don't know, 10 or 20 swap operations, or whether to replace this by one mechanical move. Yes, that's a possibility that one has on this platform. Yeah, but of course, yeah, as you have seen, this motion is. I mean, I'm impressed. You know, it's a 1 millisecond. You can do the whole algorithm in still in 1 millisecond. Yeah, but of course, it is 1,000 times slower or even more than the single qubit operations. Yeah, please.
The qubits are represented in 2D here. Is it possible to also have them in 3 dimensions?
Yes. So I showed this picture here. This is the Eiffel Tower, and you can think about this in 3 dimensions, for example, also representing a certain chemical molecule. Yeah? If you have a certain conformation, let's say, of a molecular complex, you can dial it in, you can put the qubits, and of course, the distance between the qubits is micrometers, yeah? But they have these very strong spin-dependent interactions, so you can use this platform also to simulate, in that sense, quantum chemistry problems, for example. Yeah. Yes, please.
It's kind of 2 questions in one. So, with fidelities, maybe kind of the atoms moving around, move the atoms around, tracking the fidelities over time, or just
well,
tracking
yeah.
atoms measured. And also just a simple quantum circuit, so I don't know, depth of 5 or something like
yes.
that. Like
So,
ballpark ideas of how much
yeah, so I mean, if you go to the paper of the Lukin group, you find the fidelity measurement of this, I mean, moving back and forth, yes? And there is a little bit of loss, but it's still, I think, on the 99% level, yes? So it's actually surprisingly good, yeah? So the question was, what is the infidelity due to this motion here? Yes. Okay. And there was another question here. Yes.
I have actually 2 questions. One is, when I have some algorithms that need a lot of qubits, you may have to leave the single, let's say, 3D array of the atoms. So what technology could be used to do this? An optical coupling or thing? Because this coupling should be in some way also coherent.
You mean how we are scaling to even larger sizes? Yes. Okay. So these qubit arrays at the moment are limited by laser power and some linear optics things like the field of view of some microscope objectives. This will limit it to about 10,000 qubits, I would say. Yeah? And at that moment, we have to think about laser technology, but we are not at this limit yet. Yeah? So at the moment, we are at 300, 400, 500 qubits, but it's foreseeable, yeah, that we will have to think about going beyond that 10,000 qubits. Okay, and then I mean it's an optics problem. Yes, you have to combine various laser beams, yeah, to scale it up. I mean. And you eventually have to keep these areas close to each other. But I mean, what already has been established is, let's say, one area of qubits here, another area of qubits there, with a second type of optics, and you shuttle them between them, yeah, if you want. Yeah? So it's a matter of stitching these things together. Yes, and I would say there's room for clever classical optics ideas, and we are actually teaming up with the Fraunhofer ILT in Aachen to build a setup that we think has some advantages, but I can't talk too much about it. Yes.
Because the second question is, there is a kind of ratio for, let's say, fault-tolerant or error-corrected qubits. Would you say your ratio is about 1,000?
No. Okay. So Error correction codes have been implemented. I didn't talk about it here. It has been demonstrated that you can use the Steam code using 7 qubits and the surface code. And it has been shown that if the depth of the surface code increases, the fidelity increases as well, yeah, of the logical qubit. And the depth of this logical qubit, the realization by the physical qubits, was reaching 7 now. Yeah? So it's not thousands. It's about 100 or so or less. And it has to do also with the fact that the errors that occur here in part are qubit loss errors, which means that the qubit leaves the Hilbert space. It drops into another state that is not part of your computational Hilbert space. And if it does that, you can detect this actually extremely efficiently. And the error correction schemes for this kind of error have a much lower threshold than normal error correction codes have.